Okay, thank you.
Yes, thank you, Professor. Thank you very much for your nice talk. And it is motivated us for many young researchers. Thank you very much for your talk, Professor.
Thank you.
Thank you. Any questions from the participants?
Professor Patil.
Yeah, Professor.
It is a courtesy goes to Professor Vichian.
Yeah.
That during this period, especially tomorrow we are going to celebrate the National Mathematics Day.
Yeah, yeah.
And
yes,
he's sharing about the Ramanujan and his contribution.
Yeah,
so
very much.
we must give him big applaud for his work. He's a very outstanding worker in the field of number theory.
Number theory, yeah.
Yeah.
Yeah, it is very benefited to the students also, young researchers on the number theory too.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes, sir. Yes, sir.
Thank you, Professor. Thank you very much. Thank you.
Thanks, Professor Patil, and thanks, Professor Vichian, for sparing some valuable time from your busy schedule to share with us your knowledge domain. So please, organizer.
Sir?
Yes, just once a request is there on my behalf.
Yes,
with the permission of the Chief Patron, Professor B.S. Bist and Dr. Dawmani Christopher, and the respected fellow from the Patron Committee, because Professor Zenaida is waiting since the beginning, facing some technical issue, as well as some confusion, I think, somewhere created, because there are the two similar names are visible in front of me. I think on behalf of the administrator level, Lilia and Liliana. These two fellows are here. Some error occurred. That's why Liliana unmuted, and Lilia was unmuted. So please give a 1 or 2 minutes to Professor Zenaida to say a few words.
Thank you very much. Дорогі друзі, перш за все вам велике вітання з України. По-друге, я хочу сказати, що серед математиків існує така приказка, що наполегливо працюючи над якоюсь теоремою, ми її доводимо вдень, але потім її вночі спростовуємо. Це дає все то, що ми зможемо з вами говорити, що математика для бізнесу є дуже цікавою, дуже необхідною, бо без математичного підходу складно розглядати та приймати управлінські рішення у будь-якій сфері діяльності. І через те сьогодні ми бажаємо, щоб у вас все-таки всі ваші виступи, всі ваші знання лягли якраз у розвиток національних економік. А зараз я попрошу включити Лілію Кухарську, щоб вона переклала.
So firstly, we want to thank you that we are online, that we are muted. So I'm gonna translate Professor Zenaida. There is a saying among mathematicians, working hard on a theorem should be proved during the day and refuted at night. This principle is useful not only for mathematicians, but also for business. Without a mathematician approach, it is difficult to consider and make management decision in any field of activity. And today, the economy requires accurate calculation and forecasts. We want the results of today's speech and the researcher form the basis of economic decisions and the development of national economies. Use math and don't make mistakes. Good and fruitful work and creative inspiration. Thanks a lot.
Thank you. Thank you.
Thanks, Professor Zenaida and Lilia, for helping Professor Zenaida convey the message. And Dr. Amut please take the mic and please go ahead with the proceedings.
Yes, sir. Yes, sir. Okay, Professor. Shall we proceed with Dr. Liliana?
Yeah.
Shall I hand over the session
Yeah,
to
sure,
Dr.
sure,
Liliana,
sure,
Professor?
sure.
I request Dr. Liliana to chair the session.
Okay, I'm here now. I think everyone is clear why, and myself too, why the administration unmute me, stay, and I say no, I'm quiet, no. Okay. Then let me present our next speaker. It's about Professor Ali Agul from Turkey. What I can say is it's a long and a big CV and very rich. It's about a professor, associate professor since 2016, over 100 EC papers, different research stages from different states, as Romania. Now I see that was in Romania, Valencia, Spain, Texas, USA, Missouri University, and go on. By me, I meet Professor Aliago. I have this honor to be invited speaker to other conferences, international conferences. I can say that Professor Aliago is the invited speaker over 20 conferences, and now I will let him speak how his wonderful speech for today.
Thank you so much, dear friend, Professor Liliana. I'm really happy to be in this conference, and I would like to thank the organizers for this nice conference, and special thanks to my friend Liliana. And I will like to share my talk. I'm working in Siirt University, Turkey. I will talk about the solutions of fractional and fractal fractional differential equations. You can see my presentation, right?
Yes, it is visible.
Okay, thank you. Let me make large. I will talk about the fractional calculus and an effective method, reproducing kernel method, and fractal fractional differential equations, and I will give some applications. At last, I will discuss some suggestions for researchers. Reproducing kernel space is a spatial Hilbert space, and in recent years, there are many papers on the solutions of the nonlinear problems with the reproducing kernel method. In the early development stage of the reproducing kernel theory, most of the works were applied by Bergman, and then the second development stage of reproducing kernel theory was started by Merkel. And also he proved the reproducibility property. This is very important property in this method. Then the third development stage of the reproducing kernel theory related to the Arons in 19. This paper is very important related to theory of the reproducing kernels. When modeling physical process, clear advantages occur if the problem can be formulated in Hilbert space H of differential function set E. In this book, Ming and Swen-Ninger nonlinear numerical analysis in the reproducing kernel space, there are many applications of the reproducing kernel method. The introduction of the reproducing kernel Hilbert space W sub 2 super M and W sub 2 super M comma N by Sue and Lin led to an explosion in application of the reproducing kernel Hilbert space method to many areas of mathematics, ODE, PD, fractional, and many other differential equations can be solved by this method. Let this be a Hilbert space of real functions defined on an empty set E. A function K is called the reproducing kernel function if we have these two conditions. Last condition is important, is the reproducing property. Let m be positive integer. The space w sub 2 super m consists of functions f such that m minus first derivative is in AC. It means absolutely continuous functions. Then the m derivative should be in L2. We have the inner product, the general case, like this. If we choose m equal to 1, we will obtain the simplest space w sub 2 super 1. In this space, our function is absolutely continuous, and the first derivative of f is in L2. And this is the reproducing kernel function of this space. There is an important thing in this method that is absolutely continuous. If function said to be absolutely continuous in the sense of category, then the following conditions hold. In this case, we can say U is in AC of D. For historical accuracy, we should note that the characteristic original definition was slightly different. However, it's demonstrated that characteristic definition is equivalent to the preceding definition, just as the space AC of AB plays a central role in the theory of reproducing kernel Hilbert space method. I suggest this paper. There are many clear things about the absolutely continuous functions. We say that a function U belongs to the binary space W sub 2 super M super 1 comma 1, and we write this space, this function in this space, and we have these three statements. This is our inner product. We say W sub 2 super 1 comma 1 is a reproducing kernel Hilbert space, and we have the function of this space like this. We know that R is the reproducing kernel function of W sub 2 super 1. Defining the binary spaces W sub 2 super M comma N is technically more difficult than defining the space W sub 2 super M. Okay, it means when we try to solve the partial differential equations, we need binary spaces W sub 2 super M comma N. And for ordinary differential equations, we need W sub 2 super M. This shows us that with reproducing kernel method, if you want to solve the partial differential equation, it's harder. It takes more time, and we need to get more reproducing kernel functions, and we need to construct the binary space, so it is harder to solve the PDE, fractional PDE also. Another important point is this. For example, if Ft is NC of D, then we cannot say F is in AC of D. In some papers I saw, they just say Ft is absolutely continuous, and it means that F is also absolutely continuous in D, but we prove that it is not okay. This is a basic example. Let phi be phi of x be any continuous non-over differential function on 0, 1, and define a function f by fxt is equal to phi of x. Then we take the derivative with respect to t, we will get 0. And this is belong to AC of omega. However, f does not belong to AC of omega. This is our basic example. When we talk about the fractional calculus, we talk about first the Caputo fractional derivative, and this derivative was introduced by Michel Caputo in his 1967 paper. In contrast to the Riemann-Leibel fractional derivative, when solving differential equations using Caputo's definition, it is not necessary to define the fractional order initial conditions. Then we can have you see the Caputo derivative. After Caputo, some other fractional derivatives have been presented, Caputo, Fabrizio, and Tangana-Belliano derivatives. The fractional calculus was enhanced in the recent years, and it was proven that it may be used to clarify the physical problems. This is some papers related to the fractional differential equations with the reproducing kernel method with some co-authors. And in these papers, we use the Caputo fractional derivative. These papers also. Then Caputo and Fabrizio presented a new fractional derivative in 2015. And then Atsangana and Belliano in 2016 presented a new fractional derivative. In this derivative, they used the Mittag-Leffler function. After that, we tried to apply this method to fractional differential equations with the AB derivative, and we constructed these papers with my co-authors. And then in 2017, I saw a paper that discussed the fractal fractional differentiation integration by Abdullah Tangana. We can say the fractal derivative is a natural extension of Leibniz derivative for discontinuous fractal media. It can be categorized as a spatial local fractional derivative. Applications of the fractal derivative to fractal media have taken also much attention. Then with some authors, we tried to focus on the fractal fractional differential equations, and we constructed these papers. Fractal fractional differential equations are very important topics nowadays, and we investigate the fractal fractional differential equations by the reproducing Kerner-Hilbert space method. This method calculates the numerical solution and is of great attention to many branches of applied science. And many works have been dedicated to implementation of this method. Okay, this is, we consider problem 2 and subject to the initial conditions. These derivatives are fractional derivative of Caputo sense. F is non-continuous function, U is the unknown function. This is the variable order fractional differential equation. Fractional calculus has attracted many researchers successfully in different disciplines of science and engineering in recent years. One of the main advantages of the fractional calculus is that the fractional derivative provides a superior approach for the description of memory and hereditary properties for many materials of process. And many methods have been applied to solve the fractional differential equations. And these are some related works. Based on the investigation, it's easier to understand the physical meaning of variable order fractional calculus and better to know how the variable order fractional operators are applied in physical process. We eagerly attempt to study numerical methods to variable order fractional differential equations also, and we try to get the numerical results. Because of we don't have much time, I'll just pass some pages. This is the basic definitions of Riemann-Liouville fractional integral and the Riemann-Liouville fractional derivative. And this is the Caputo derivative. I discussed the difference between them. And this is for the problem, the reproducing Kerner-Hilbert spaces that we need. We define H sub 2 super 1. U is absolutely continuous, U prime is in L2. We get the kernel function of this space. Actually, we need this space for the range of the problem. This is the second space. Similarly, we get the reproducing kernel. But because our problem is a fractional PDE, then we need 4 reproducing Kerner-Hilbert spaces and 2 binary reproducing Kerner-Hilbert spaces. So it's more complicated than the fractional ODE. This is the third space we need. And this is our kernel function. And this is the fourth space that we need. As you see, in this space, our space should satisfy the initial condition also. Then our kernel is different. And this is the binary reproducing kernel space that we need for the domain. And here we need the completely continuous functions, and we need to our function satisfy, our space satisfies the initial conditions also. This is the inner product, and this is the kernel function. This is the second reproducing kernel binary space that we need for the range, and similarly we define the inner product and the norm. and we get the kernel function in a similar way. Then we get the numerical results. This is just an example related to variable order fractional differential equations. This is our first problem. And this is the second problem. We have the exact solution. This is the third problem for the variable order fractional PDE. Yes, another important thing, if you want to apply the reproducing kernel method, we have to homogenize the conditions. After homogenizing the conditions, we obtain these results, approximate solution and exact solutions for different values of x and t, and the results are good enough. These are some results. And this is the fractal fractional differential equations with the power law kernel. In here, we use fractal derivative by 15, you can see. And we define FFP, fractal fractional differential equations with the power law kernel. Then we use also the Laplace transform to get the exact solution. We have the relation for the Caputo derivative. We can write the Caputo derivative using the convolution. And we have the Laplace transform of this by 19. And also we have the relation between the Riemann-Liouville and Caputo derivative S. Now, this is our first problem. We use the relation between the classical derivative and the fractal derivative, then we get Riemann-Liouville derivative by 24. We use the relation between Riemann-Liouville and Caputo derivative, then we get 25. This is our second example. We apply the same process. We get the Riemann-Liouville, and after that, we use the relation, we get the Caputo. Then we apply the Laplace transform, and we get Ly of x. And we are ready to apply the inverse Laplace transform, and we get the solution. This is another example. We use the same process, and we obtain the exact solution. After that, we apply the reproducing kernel Hilbert space method to the fractal fractional differential equations. In here, we obtain the reproducing kernel functions again, so I will not spend much time in here. Then we solve the problem in A2, A sub 2 super 2. And this is our problem, 38. We construct phi I is equal to Cxi. Our C is the reproducing kernel function. And we define phi I is equal to a joint operator phi I. And we use the Gram-Schmidt orthogonalization process. Then this is the main theorem. Assume that Y is the exact solution of the problem. Then we get 40. Let's see the proof. The proof is very easy. We use the complete system. We use the property of the adjoint operator, and we use the reproducing kernel property, and we get the desired result. And we construct the approximate solution like this. Then we obtain the numerical results for different values of alpha and beta. Alpha is the fractional order, beta is the fractal dimension. So in this result, you can see the effects of the fractal dimension on the problem also. And these are some suggestions. Fractional order difference equations, reproducing Sobolev spaces, reproducing kernel Banach spaces, solutions of fractional differential equations on time scale by reproducing kernel method. I suggest these topics to the researchers. I will also try to focus on these problems in the future. So thank you so much for your attention.
Dr. Liliana.
Thank you very much for your nice talk. Anyone, if have any questions? No one? No one is interesting about the fractional calculus?
I think people are here, those who are working in the field of fractional calculus, especially
Yes, I think we have here.
yeah, especially the from Rajasthan domain of India, a very good worker on the fractional calculus. If NK Saha is here, NK Saha is working on fractional calculus. Anyway,
Great.
Dr. Ali, Dr. Liliana, please perform your duty as a chairperson to Professor Ali.
Then thank you very much for your talk and for your presence here.
Thank you. Thank you so much for your.
Thank you, Professor Ali, for
Yes.
your wonderful contribution. Even then, you have a very lengthy 112 slides are with you. Within 20 minutes, you have just computed quickly.
Yeah, I passed many things because first I asked to my friend Professor Liliana. She told me you have 45 minutes. So I presented for
Okay,
45
no
minutes.
problem. Next
Then
time,
I
next
learned
time.
that I have 20 minutes. Then I passed some pages. It's no
No,
problem.
no, yes, yes. Actually, what happened, a lot of number of speakers are here. So anyway, you have nicely shared the work that you have carried out. And during the next conference, definitely we would like to listen with the very good workers are here in India, especially from Rajasthan domain, those who are working in the field of fractional calculus. And definitely they all will join to listen your talk in the next conference that we will organize hopefully in the month of March. And be ready. I will invite you once again. And one thing is there, one of my convener is Professor Dr. Muge Sakar. She is from Turkey. She wants to say something. You know very well.
Yeah, she's my friend. She's my
Okay.
very kind friend.
Yeah, Dr. Muge Sakar, please say a few words. Unmute your first. Please unmute. Please unmute. Dr. Amutha,
Maybe
please
she
unmute.
cannot unmute. Maybe she cannot unmute.
Yes, sir. Yes,
Dr.
sir.
Amutha, please unmute
Yes,
speakers
I'm here,
especially.
sir. I'm here, sir.
Okay. Hi, Professor Ali.
Hi, dear friend.
Hi. Thank you, Professor Ali, for your excellent presentation. I know Professor Ali since the time of PhD in our student time. Yes, I know Professor Ali. He is so hardworking and professional in his field. He is also very sincere. I am so happy to see him in here, and I hope that to see him in our next conferences. Again, thanks, Professor Ali. He is my best friend.
Thank you so much. I'm very happy to hear such things from you, dear friend. I'm happy also to see you here. Thank you so much.
Thank you. Thank you.
Thanks, Dr. Muge Sakar. And thanks, Dr. Ali,
Thanks.
Dr. Liliana.
Thanks.
Okay. So now I ask organizers to go for the next session, to move for the next session.
Yes, sir.
Thank you, Professor. Now I request Dr. M. Dhavamani Christopher, Principal and Secretary of the American College, Madurai, to chair the session.
Hi, friends. Happy to see you all again. It's my pleasure to introduce Monica Felicia Borisiano. That is Bota, works at Babes Bolia University, the Faculty of Mathematics and Computer Science at Cluj-Napoca. Cluj-Napoca, the Babes Bolia University is one of the best university, and you can call it as OUBB. It's a public university in Cluj. Babes Bolia University, commonly known by its abbreviation UBB. And Monica's dissertation title is Dynamical Aspects in the Theory of Multivalued Operators. She has more than 20 ISI scientific publications and she is the Vice Dean of Faculty of Mathematics, German line specialization. She studied abroad, that is in German, for 2 years. She did her PhD in German and was invited speaker for many conferences in Europe. I think this is the first time she has been invited in India. Thank you, Monica Felicia Borisiano, for accepting our request. Over to Dr. Amuda, the organizing secretary.
Yes, sir.
Yeah, unmute Dr. Monica, please.
Monica, ma'am, you can proceed.
Yes, yes. Hello. Thank you very much for your kind invitation. I have pleasure to be here together with you today. You can hear me. Is that right? Yes. Because I had some problems with my internet connection, and that's why I asked you. So thank you very much for your invitation, and I will share now my screen in order to present. Is okay. Now I think you can see. It's okay with you? You can
Yes, it
see
is
my
okay.
whole screen, yes?
It is
Okay. The title of the talk for today is Fixed Point Theorems on B-metric spaces with applications to couple fixed point theory. I did my PhD thesis on the field of B-metric spaces, and I study various contractions on these B-metric spaces. And as the plan of my talk, first I will present some preliminary notions regarding the B-metric spaces, then some fixed point results, application to couple fixed point theorems, and then the references. Okay, first we will all know this is a very important and very well-known result in the theory of the fixed point, this Banach contraction principle, which seems very simple, but it gives us sufficient conditions for the existence and the uniqueness of the fixed point, and also provides us an algorithm to approximate those fixed points. So it's a very good tool to work it. And that's why many mathematicians start from this Banach contraction principle and extend it and generalized it in two senses, I can say. And one of it is that the contraction condition can be changed, can be extended. So we can consider, instead of this simple contraction condition, the Rice type condition, Chirich, Hardy-Rogers, or Cannon, any kind type of conditions. And we can also extend the structure of the space. So we will do both of these extensions, and we will work in a complete B-metric space